Good afternoon, friends. Today we are looking at a new topic, transformation, and our lesson for this session is a translation. To present, I'm Gala Gavin. To take you through on today's lesson outcomes, what we expect at the end of the lesson, the skills that we should have learned after the presentation of the lesson. We need to, at the end of the lesson, describe what a transformation is. We need to describe a transformation. And then we should find a translation matrix representing a translation transformation. So now, what is a transformation? In simple English, a transformation is the same as undergoing a change. For example, when we were born, we were babies. We started transforming or changing size, changing, and now we are full-grown people. So, a transformation in mathematics is a geometrical operation that transforms or maps a set of points. A set of points which we are calling the original object onto another set of points which we call the image. As a result, the position, size, and or shape can be changed in some transformations. We are going to look at two types of transformations. One, an isometry. Two, an affine. So the lesson for today is among the type of transformation which is isometries. So isometries, if the image has the same dimension, same size as the original shape, the transformation is called an isometry or a congruency. Basically, there are three congruencies: translation transformation, reflection transformation, and rotation transformation. The other type of transformation, which are affines, we'll look at them later on. We are going to concentrate on isometries and particularly a translation. So, what is a translation transformation? When we move points of an object through the same distance in the same direction, in a straight line, the transformation is a translation. So a translation moves every point of an object through the same distance in the same direction. A translation is fully described by a translation vector or a column vector, a column matrix, and it is denoted by the capital letter T. So T equals to X, Y, which is a column matrix, is describing a translation. Now, these components X and Y are movements, because we are saying a translation moves every point of an object through the same distance in the same direction. The components X and Y are movements. X represents the movement along the x-axis. Y represents the movement of a point along the y-axis. Now we should note that we should be aware of positive and negative components of the translation. Let us look at the illustration in our diagram. We have the triangle ABC, which has been translated onto PQR. Or in short, we can say triangle ABC has been shifted onto triangle PQR. Now, a translation is an isometry. We have seen that the size of triangle ABC has not changed even through the translation mapping it onto PQR. The same size of ABC is the same size of triangle PQR. In our diagram, the translation column vector, which has transformed triangle ABC onto triangle PQR, is 3, 4. By counting units along the x-axis and the y-axis. Now, allow me to show that the coordinates or the point A on triangle ABC has been shifted onto triangle PQR onto point P here. I don't know if my pointer can be seen. Let me quickly change and use the arrow. Now, the point P, as I was saying, has been translated onto the point P. Allow me to go back to the previous slide. The point A here has been shifted onto point P. Now, we are going to count the units of moving the points. The first one is counting along the x-axis. Now, from A to where P is, we are going to count 1, 2, 3 units. 3 units, 3 movements. And so we have 3 as a component along the x-axis in the column matrix. Now, on the movement, we have moved from A to P in the right direction. So, movements in the right direction are positive movements. Remember, previously I said we should take note of positive and negative movements of points. So, point A along the x-axis, or parallel to the x-axis, the movement at A, there is no movement. when we move a square from A, that is one movement. So we are counting 3 movements, 1, 2, 3, giving us 3 as the x component. When we move upward to where point P is, we'll be moving in the vertical direction or along the y-axis. So we are moving 1, 2, 3, 4 units. Therefore, triangle ABC has been translated or transformed onto triangle PQR by the translation matrix 3, 4, meaning that along the x-axis, the horizontal axis, we have moved 3 units to the right. And along the vertical axis, the y-axis, we have moved 4 units upwards. Along the y-axis, we are moving upwards. So right movements and upward movements are positive. That is why we have positive 3 as the x component and 4 as the y component. The same diagram which is represented there. Now, you will see that all the points will move in respect to the counting or the column vector 3, 4, meaning that all the points will be moving 3 movements or 3 units along the x-axis and 4 units along the y-axis. Let us observe the movement of point B. So point B along the horizontal axis, the x-axis, it is moving 1, 2, 3 units. We need to stop at where we have the corresponding point, the line where we have the corresponding point to B, which is point Q, because point Q is corresponding to point B. So we have moved 3 units along the horizontal axis. So we are going to start counting upwards up to the point Q to see that also point B is moving 4 units upwards onto point Q. So we are moving 1, 2, 3, 4 units. The same movement C will respect. We are going to move 1, 2, 3 along the horizontal axis and also 1, 2, 3, 4 along the vertical axis. So we can conclude that point or triangle ABC has been transformed onto triangle PQR under the translation 3, 4. Now, the translation vector can be found by counting and also by means of a formula. So, the object here, the word object stands for any point of the original object before transforming, plus T stands for the translation vector or the column matrix. So when you add the translation vector representing the object point and the translation which is mapping the points onto the object, we get the image point. Implying that when we make T the subject of the formula, we are going to have translation vector is equal to image minus object, meaning that the column matrix representing the image point subtract the column matrix representing the object point. Then we are finding the translation, which is mapping the original point onto the image point. I will leave you with a task to write down the translation vectors which move triangle ABC onto each of the positions of the triangles labeled A, B, C, D, and E. The triangle ABC is this one. As you can see the cursor there, triangle ABC is this one, which has been shifted or translated onto these triangles. Triangle labeled A, B, C, D, and E. I will give you 3 minutes to do so, and later on I will show you the slide for the solutions to confirm your answers. All right, let us check our answers. So if you got any of what you are able to see there, triangle ABC has been mapped onto triangle A by 0, -9, meaning that there are no movements. There is no movement along the x-axis. And the -9 there means or implies that we are moving 9 units downwards. 9 units downwards along the y-axis. Triangle ABC has been mapped onto triangle B by the matrix, the column matrix 10, 2. 10 units along the x-axis and 2 units along the y-axis. So you can confirm with the rest and see if you are correct. In the interest of time, I will leave you here. Thank you for your attention. This is the end.